Welcome to Networks Professionals.
Welcome to this explainer. Look, if you've ever wondered how developers train AI models to actually survive out there in the messy, completely unpredictable real world, well, you are in the exact right place. Because as we all know, the real world is definitely not some pristine, perfectly lit laboratory. It's chaotic, it's constantly changing, and it almost never gives you the perfect angle. So today, we're exploring a concept that basically acts as a rigorous, no-nonsense boot camp for artificial intelligence. We're talking about mastering data augmentation. It's an absolutely fascinating process that bridges the gap between perfectly controlled data and our actual reality. Let's jump right in.
All right, let's kick things off with Section 1, the AI memorization problem. Because, as it turns out, sometimes an AI can be a little too good at exactly the wrong things.
So what happens when an AI just memorizes the answers? Imagine an AI model like a human student, desperately cramming for a huge final exam. If you only hand that student the exact same practice test over and over again, they aren't actually learning the fundamental subject matter, right? They're just memorizing the specific pixel patterns to get a passing grade in that controlled environment. Sure, that AI student might completely ace every single practice exam you throw at it, but when real-world conditions inevitably change, unexpected bad weather, weird shadows, unusual camera angles, that model is going to completely fail. It simply doesn't have the underlying understanding it needs to adapt. And that brings us to a really stark contrast in AI training. On one hand, we have overfitting. Overfitting happens when the model just lazily memorizes the exact pixels it was fed during its training phase. The model essentially becomes brittle. It only knows exactly what it's already seen. So it hasn't actually learned what a car is. It's only learned what that specific car looks like in that specific lighting. On the flip side, we have generalizing, which is the ultimate holy grail of all AI training. A generalizing model successfully adapts to entirely unseen conditions. It doesn't just memorize the image, it actually understands what it's looking at regardless of the context, the background, or the angle. It extracts those core features and applies them to brand new situations.
So how do we fix this? Enter data augmentation. This is the ultimate solution to that memorization problem. It's basically the process of artificially expanding a training dataset by generating modified copies of existing images. By taking our original dataset and creating hundreds or even thousands of altered copies, we actively prevent the models from memorizing those specific pixel patterns. This dramatically reduces the risk of overfitting and quite literally forces the AI to generalize. It learns to recognize the fundamental shape, the structure, and the actual identity of the object, ensuring it can survive those unseen chaotic conditions we really need it to navigate.
Moving right along to Section 2, shifting shapes and colors. This is where we start throwing some serious visual curveballs at our AI. The first vital tool in our little boot camp involves geometric transformations. This is all about altering the spatial properties of an image. Imagine us acting like a highly demanding drill sergeant in a digital obstacle course. We start out pretty simple, just flipping the images to create horizontal or vertical mirrors, and the reason we do this is absolutely critical. Think about it. If every single image of a car in our data set happens to be driving to the right, the AI might wrongly assume that a car driving to the left is something else entirely. Flipping ensures the AI doesn't become stubbornly reliant on objects facing one predictable direction. But we don't just flip images. We actually rotate them. And the specific angles here, like 15 degrees or 45 degrees, are really interesting. In the real world, things are almost never perfectly framed and sitting completely upright, are they? Security cameras get bumped, drones tilt in the wind, humans hold their smartphones at completely random, wonky angles. So by purposefully spinning these images during training, we successfully break the model's expectation of perfect, upright alignment. The AI basically learns to tilt its own metaphorical head. Next up for geometric transformations, we've got scaling and cropping. This means zooming in, zooming out, or selectively cropping out sections of the image entirely. When we zoom in or crop out a piece, we are aggressively forcing the AI to focus on very specific features rather than relying on the comfortable context of the whole pristine picture. It has to recognize the core subject, whether it's a tiny speck way off in the distance or zoomed all the way up against the camera lens. It strips away the easy context. Then we escalate the boot camp by messing with the lighting. This brings us to a highly effective technique called color jitter. Color jitter involves directly shifting pixel intensity, specifically modifying the brightness, the contrast, and the saturation of the training images. Because, let's face it, the real world is absolutely never a perfectly lit photography studio. By jittering these colors, we simulate incredibly unpredictable, wildly varying lighting environments. We're making sure our AI can see its target clearly at high noon, in heavily shadowed alleys, or even during a dim twilight. All right, section 3, adding real-world noise. Now it's time to step completely out of the clean lab and introduce some actual damage to our data. We really have to toughen this model up. Our first technique for adding noise is blurring, specifically utilizing something called Gaussian blur. You've almost certainly taken a blurry, out-of-focus photo before when something was moving just a little too fast, right? Well, cameras capturing data out in the field do the exact same thing. By intentionally injecting this noise and adding Gaussian blur to perfectly clear images, we are actively teaching the model how to handle out-of-focus subjects without completely panicking. It essentially learns to rely on broader outlines and core shapes when all those crisp, fine details vanish.
Another super powerful method is known as cutout, or random erasing. Now, this one is fascinating. We literally take random blocks of the image and just mask them out entirely. We just delete rectangular blocks of visual data right out of the picture, leaving these solid digital voids. Now, that might sound completely counterintuitive at first, but it serves a massive purpose. It forces the AI to recognize objects that are only partially visible, because in reality, things overlap. A pedestrian might be half hidden by a parked car, or a stop sign might be blocked by a branch. The AI still needs the structural knowledge to confidently identify the pieces it can actually see.
Let's move to section 4, advanced image mixing techniques. Because if blur and missing pieces weren't enough, wait until you see these composite samples. When we look at advanced mixing, two specific methods really stand out: mix-up and cut-mix. Mix-up smoothly blends two completely separate images together at a specific weighted ratio. Think of it kind of like taking a semi-transparent image of one object, say a dog, and laying it directly over an image of another, like an airplane. It creates this ghost-like combination that forces the model to untangle conflicting signals. Cut-mix, on the other hand, is way more aggressive. It involves literally cutting a patch of pixels from one image and pasting it right onto another. Both of these create entirely new, almost Frankenstein-level composite samples that severely challenge the neural network.
And finally, section 5, top augmentation tools. So, practically speaking, how do developers actually build this rigorous AI bootcamp?
Well, modern developers rely on a pretty specific arsenal of specialized tools. First up is Augmentations. This is a widely used, incredibly high-performance library that packs an arsenal of over 70 specific computer vision transformations. It's just an absolute powerhouse for building complex pipelines. Next, there's the Keras Image Data Generator. This is a much more straightforward built-in option right inside TensorFlow, and it's heavily utilized for setting up simple classification tasks quickly. And finally, developers consistently rely on the RoboFlow augmentation docs. This acts as a comprehensive guide for navigating the whole landscape, helping developers choose exactly the right transforms for their highly specific datasets.
So as data augmentation continues to artificially expand these datasets and bridge that massive gap between perfect lab data and our chaotic reality, it leaves us with a pretty profound question. If we can successfully teach AI to see clearly through this much artificially generated noise, what complex visual challenges and real-world chaos will these battle-tested models conquer next? Thank you so much for joining me for this explainer. I really hope these concepts helped clarify exactly how this vital technology works behind the scenes. Keep learning and keep questioning the data.
Thanks for watching.